Kugule, and I'm a PhD student in the computer science department here at the University of Memphis. I work with Stan Franklin and his cognitive computing research group on LIDA. Those of you that have never met Stan, he's right here. We're lucky enough to have him. He is the father of LIDA, and he'll probably make sure that I don't make any big mistakes over here. He'll probably raise his hand or slap me or something like that. So today the presentation is Learning in LIDA, and the basic structure of this presentation is the first part of it. I'll go over some of the high-level details of what LIDA is, just conceptually. Second half of it, I'm going to dive into some more details about the modules that make up LIDA, the functional components that make LIDA what it is. And then I'll conclude by talking about the different learning mechanisms in LIDA and our conceptual commitments that are relevant to learning in LIDA. So first, what is LIDA? LIDA stands for the Learning Intelligent Decision Agent. Now, I'm sure that there's at least one person in the audience here that's saying, wait a second, LIDA stands for the Learning Intelligent Distribution Agent. That was so 2 years ago. It's Learning Intelligent Decision Agent. The marketing guy said that we got to change. So this is what it is now. And now that we got that out of the way, I'm going to go over various just high-level characterizations of LIDA. And this is just listing them off. If you have any questions, I'm going to be going into more details about this as we go along. So first, LIDA is a conceptual model of minds, where we define minds as control structures for autonomous agents. LIDA is a systems-level cognitive model, or another way of saying this is that it strives to be a unified theory of cognition. LIDA is biologically inspired, meaning that we look at psychological theories, we look at neuroscientific theories, experimental results, and these different things have influenced the development of LIDA, and we try to explain these different theories in terms of LIDA. LIDA models functional consciousness, which is also known as access consciousness, by implementing and fleshing out some significant portions of global workspace theory from Bernie Bars. I'll go into this in a lot more details, but this is really, really relevant because one of our strongest conceptual commitments related to learning, the conscious learning hypothesis, states that all significant learning requires consciousness. Finally, LIDA implements or views cognition in terms of cognitive cycles, this frequent perceiving and acting on the environment. And I'll go into more details about this later, but you can think of these cognitive cycles as cognitive atoms, where multiple of these cognitive atoms come together to implement higher level cognitive processes like planning or reasoning or problem solving. So first, LIDA models minds, not brains. And it's not that we have anything against brains. We love brains. We draw inspiration from brains. But what you're not going to see in LIDA, you're not going to see neurons and synapses and ion channels and all these different things that make up brains. Minds we consider a more general thing where brains are just one way of instantiating minds. Minds could also exist, for example, in software. So the definition we're using of minds is control structures for autonomous agents. And autonomous agent has a very specific definition. So the definition that we're using is that an autonomous agent is a system situated in and part of an environment which senses that environment, acts on it over time in accordance with its own agenda, so as it may affect what it senses in the future. And this particular definition came from a 1997 paper by Stan Franklin and Art Gracer. And the paper was entitled, "Is an Agent or Just a Program? A Taxonomy of Autonomous Agents." One of the most significant questions that minds have to answer, autonomous agents have to answer, is what do I do next? And that's sort of, you're going to maybe see that as we go forward. So LIDA is a systems level cognitive model. So it models cognition end to end. It models it from incoming sensory stimuli to outgoing actions, and it then includes all the different supporting cognitive processes in between. It tries to supply a unifying framework for cognition, a theory for explaining agent behavior and the different underlying processes that help to explain agent behavior. One thing to point out is that LIDA is not only a cognitive model that tries to predict, but it also, we try to build useful things with it. It tries to solve engineering tasks of building agents that accomplish something useful in the world. So biologically inspired. Here's a small list. It's not inclusive of all the different theories that we've looked at or tried to accommodate in LIDA. But some of the significant ones that I'm going to just sort of highlight here is global workspace theory. I'm going to talk more about this. It's very, very important to LIDA. The researcher is Bernie Bars that first came up with this back in the 1980s. Perceptual symbol systems, another very important theory that's influenced LIDA, related to grounding representations and concept learning. Ideomotor theory from William James, that's been very influential in how we think about voluntary action selection and deliberative thought. And constructivist learning has had a big influence on some of our modules, in particular our procedural memory module, which this theory is for Jean Piaget and Gary Drescher. He fleshed it out with the schema mechanism. So global workspace theory, again, I mentioned functional consciousness, and some of you might be thinking, what's functional consciousness? So what's in contrast to is phenomenological consciousness. We're not trying to say what it is like to experience something, what the qualia is of consciousness. What we're trying to say, understand is, how does consciousness support things like attention and the recruiting of resources so that an agent can do meaningful things and take actions in an environment. So global workspace theory, it views consciousness as a collection of specialized unconscious networks called processors. So here in the diagram over here, this group of unconscious processors, of which a subset of them, of these unconscious processors called contexts, they try to influence the different things that come to consciousness, that conscious contents. And so there's different kinds of contexts. This is by no means a complete list, but you might have goal contexts that are trying to shape our intentions or what we want at a given time. Conceptual contexts that shape how we think about the world, and perceptual contexts that might shape how we see the world. These different contexts, which are coalitions of processors, they could either compete with each other or collaborate together for some particular goal of bringing a particular kind of conscious contents into the global broadcast, where what happens is that these different conscious contents, when they compete, the one that wins goes back and is received by all the different unconscious processors that are listening for this broadcast. Another way that I've heard global workspace theory talked about is in terms of a blackboard architecture, where you can imagine there's one marker that everybody is competing to use, and the winner gets to actually write something on the board where then everybody gets to see it. So here's the cognitive cycle. And so you can see, so thinking back to our definition of an autonomous agent has to sense the environment, has to then act on the environment, which then influences what it sees, and then the next time step, what it sees in the future. So here's the different connecting points to the environment, and all of this stuff in the middle, which is the, what we call the 3 different phases of the cognitive cycle. These are our control structures. So as the agent senses the environment, it first goes through this process of trying to figure out what it all means. It tries to build up a current model of its situation to understand it. But there's way more in that current situation than it can attend to at any given time. So it has to filter what the most salient pieces are of this content. And then once it figures out what those most salient pieces are, it gets broadcast out, where that recruits all these different resources. The agent's able to select a particular action based upon that broadcast. And also, that broadcast content supports learning in all the different modules. And so it goes, this keeps on going and going. And the more complex the cognitive process you're trying to model, the more of these cycles that you might need. So a deliberative process might take many cycles to actually conclude. Okay, so now I'm going to go through each of the different modules in a little bit of details to give you some understanding. So this diagram, the first thing I forgot to mention this, there is one other characteristic of LIDA. It's very complicated. It's a complicated model. But this diagram shows all the different interactions that we have between the different modules, and also shows so that the blue coloring is a long-term memory module. So we have perceptual associative memory, for example, which is our recognition memory, spatial memory, which we have our spatial maps, so forth and so on. The tan color is a short-term memory module, and then you can see these orange-colored arrows, this is related to the conscious broadcast going out, and then that conscious broadcast supports learning in different modules. We also see other kinds of connections that show the interactions between modules, and so I'll explain these as I go. Another thing I'm going to do is I'm going to show you, so we've talked about 3 phases for the cognitive cycle. We've got this perception and understanding phase, this attention phase, and this action and learning phase. I'm going to show you where all this stuff fits in relationship to the cognitive cycle. Okay, so the first of our modules that we'll talk about is the short-term memory module, sensory memory. Sensory memory is the interface between the environment, whether that be the internal environment or external environment, where internal environment is directed towards the body of the agent, the internal processing of the agent, and the external are things that it might be viewing out external from its body. What happens is that the agent, there's sensors, the agent would use its sensors, and from those sensors it would encode modality-specific representations. Each different modality, whether it be visual, auditory, tactile, whatever, would have potentially different kinds of modality-specific representations. These representations then could go on to activate things in our recognition memory, perceptual associative memory, through the use of different feature detectors. It also could be integrated into the preconscious workspace. I'll go into these things in more detail later, but going into the preconscious workspace, then we can start seeing multimodal representations that combine modality-specific representations into a larger perceptual scene. To maybe make this a little more concrete, let's talk about an example. So let's say that your agent has a sensor that's pointed at its body for how long it's been since it ate. And there might be other things that are more complicated, like hormones and things like that too, if you're talking about a biological agent. So your agent says, okay, well, it's been 8 hours since I ate, and there's these different hormones that are going on. This stuff builds a modality-specific representation that could then activate a, what we call a feeling node for being hungry. So this feeling node then gets activated, and then eventually would end up potentially in the preconscious workspace itself. There also, with this feeling that's going on, you might have other things that are going on where I'm visualizing a scene or smelling maybe a cake or something like that that might be relevant. All that stuff goes into the preconscious workspace. Perceptual associative memory, this is the recognition memory in LIDA. So it contains different representations for concepts and the relationships between concepts, where those relationships are themselves concepts. The representations, I've already explained how some of them can be activated by feature detectors. So inside of our sensory memory system, we might have feature detectors that are activating low-level things like, the presence of a color, for example, or a horizontal line, or, as I already talked about before, recognizing the situation of hunger and activating this hunger node in PAM. The concept nodes themselves are related to each other potentially, and so when one of them gets activated, it can also pass activation to another node as well. So there's 2 different ways of passing activation. Once activation gets above a certain threshold, these concepts that are activated would then go over to the preconscious workspace itself, where it would intermingle with other representations. Okay, so the preconscious workspace. This is probably one of the most important things that I want you to understand, because this is where so much stuff happens in supporting the agent's current understanding of its situation. So first off, the preconscious workspace as an entire module is a scratch pad for preconscious representations. So within LIDA, we have 2 different kinds of unconscious representation that we recognize, or make a distinction between. Preconscious representations are representations that have the potential of becoming conscious at some point, but they're not currently conscious. There are also never conscious representations that the agent will never become aware of in its conscious awareness. Things like motor plans, for example, the agent may never become aware ever of a motor plan, other than just indirectly that you're doing something. It's a short-term memory store, but it's also a high-capacity memory store. So one of the things that could very easily be confused related to the preconscious workspace is considering it somehow identical to working memory. And that's not the case. Working memory in terms of Baddeley and Hitch's working memory, it's not the case. Baddeley and Hitch's working memory is, first of all, conscious representations, and second off, it's a limited capacity store where this pre-conscious workspace could be, who knows? There's no definite limit on all the different pre-conscious things that are going on behind the scenes. Finally, it's a fusion of real and virtual cognitive content, where real simply means it's the stuff that comes from sensors, whether it's internal sensors or external sensors. Some visual representation from the world, or even the things that are coming from like the feelings of hunger, are sensors that are in our gut, for example. Those would still be real. Virtual is content that's created within the agent, like plans, imaginings, these things like that, that might resemble in some quasi-sensory way real cognitive content, but it's created within the agent, not from the sensor.
Can I ask you a question?
Sure.
Things change over time, right? So suppose you're seeing something and it changes. How does that get captured in the pre-conscious workspace?
I can try to answer that. So what we've talked about is having something like a perceptual scene that takes all these different modality-specific representations and integrates them together. As new information comes in, I would think it would override different portions of that sensory scene with the conflicting information. That's how I imagine how it could happen, but I'm not sure if we've ever really fleshed that out.
So does it categorize it and call it the same? If you're, like from different positions and it's slightly different activating in your sensory system. So it's a little bit different from a different angle of stuff. Is it like in the pre-conscious workspace that it's really the same scene? Maybe not even worried what angle it's from.
Yeah, I'm not sure. I guess I'm hesitant to say it would be always just the same scene. It's entirely possible. So a lot of our inspiration for some of our modules come from the copycat architecture. And I believe in the copycat architecture there was a discussion of multiple different interpretations of the same sensory information.
Yeah, it's not that I'm
exist.
talking about. I'm talking more about the perceptual. You're looking at something, you're walking across the room, and the hinges. Yeah,
invariance, like Gibson.
Is it the invariant form that gets in there, or
The perceptual object or the sensory representation?
Yeah, that's what I'm wondering. Yeah.
I think the answer is both.
Oh, okay. Okay. But you can put a lot of stuff in there.
Oh, yeah, yeah.
All right.
Okay, so let me just give an example to kind of flesh out how the pre-conscious workspace might be used. And keep in mind there are two different submodules in the pre-conscious workspace. I'm going to focus mainly on the current situational model, which is where all these different representations merge together to support understanding. The conscious contents queue is really related to these time-sensitive relationships. For the purpose of this presentation, I'm not going to go into it in detail. So we've talked about the sensory memory system, or sensory memory being able to send information over from the sensors of the agent, create these modality-specific representations that then intermingle into our current situational model. So for example, some of that sensory content might be related to just the division of that chair, the modality-specific representation of that chair over there. In addition, we've talked about perceptual associative memory, which is this recognition memory, could have had percepts that are already activated coming from the interactions with sensory memory. So for example, that feeling note I talked about earlier, being hungry, that could be sent over into the current situational model, again, intermingling with this larger set of representations. Once representations begin to build up in the current situational model, they then cue other long-term memory systems. So you start getting other memories coming in. For example, being hungry might cue some episode that I had of, oh, yesterday I had this sandwich and I'd really like to have a sandwich. That could come into the current situational model. Again, still pre-conscious. Finally, we have these little special purpose processors called structure building codelets, which in the next slide I'll explain in more detail. But they're really responsible for what we've called pre-conscious thought. They build new associations. For example, they might try to figure out causality between two different representations. Or they might build different imaginings. Like if I'm hungry, I might imagine this sandwich that I'll have when I'm getting home, and it might trigger structure building codes to build these representations. Or just action plan, or just plans in general, things like that that are virtual content. So codelets, they're special purpose processes. There's basically these two different varieties of codelets that we support in LIDA. Both varieties have one common feature in that they continually scan that current situational model in the preconscious workspace that we just talked about. They're looking for content that is of interest to them. And then they do different things with that content. Structure building codelets, they're creative processes, and when they see content that they're interested in, they'll start making new content or modifying that existing content in the current situational model. So for example, if my agent is stabbed with a needle or something like that to draw blood, it might associate feeling nodes of pain with the needle itself, and a structure building codelet might create a causality link to represent that relationship. Attention codelets, they're saliency detectors, meaning that what they're trying to do is each one of them has a concern that is of interest to them, and somehow reflects what's also important or valuable, relevant, these different things that are salient to the agent. So they see these representations and they advocate for them. They're almost voting for them, saying this is what really should come to consciousness next. And from that content, we build coalitions. Coalitions are these, it could be from representations from multiple different attention codelets, but it represents some particular concern that the agent might have that would compete for the right to come to consciousness. Okay, so declarative memory. Declarative memory is a long-term memory module for autobiographical events, which we call episodes. There are two different types of representations that conceptually can appear in declarative memory. Autobiographical episodes, and also semantic memories, which are facts that have lost a lot of their experiential context, meaning that you don't know when this thing happened or when I learned about this particular fact. You just remember the raw fact. So, for example, Paris is the capital of France. Now, when somebody first told you this, you might remember exactly who told you that in some particular classroom, or maybe riding on the subway or something like that. You remember exactly all of that context, or even emotions that might be attached to it as well. Over time, you get the same thing again about Paris is the capital of France. Paris is the capital of France. That gets reinforced again and again, but the context itself of how you heard about this thing doesn't get reinforced. So it decays away, and then these things become semantic memories. One interesting feature of declarative memory from a learning perspective is that it's reliant on another module called transient episodic memory, which I'm going to go into in the next slide. But I guess the main thing I want to get you to see on this slide is that learning requires an offline consolidation process. Now that sounds fancy, but in humans we might be talking about sleeping. It's just that process of, at the end of your day, all these different things that haven't decayed away get consolidated into declarative memory. It doesn't happen continually like some of our other memory systems. So transient episodic memory. Transient episodic memory, it's a short duration memory store for recent episodes. And by recent, there's some flexibility here, but we were usually thinking in terms of hours or maybe a day or so. And it supports two things. I've already talked about this offline consolidation process into declarative memory, but there's another use case that it also supports as well that we're trying to model with it. So imagine the scenario where you're parking in the same parking garage day after day after day after day. And that parking garage is the same, all the details are the same, cars might move around. You might park in a different spot every single day. And over time, all these different episodes begin to blur. They interfere with each other, where today I might not be able to remember where I parked with any reliability whatsoever, because all these other episodes just interfered with it. So to model this distinction between recent episodes, where I parked today, from the ones that have been consolidated into declarative memory and have probably lost a lot of the details of exactly where I parked, you have transient episodic memory that supports the recent episodes and allows us to access those reliably. Okay, so I've gone through this section of our LIDA diagram, which corresponds to the perception and understanding phase of the cognitive cycle. We've talked about how sensory stimulus or sensory stimuli from the internal and external environment could go to the sensory memory system to be encoded in modality-specific representations. Those representations could activate various representations in PAM, for example, using feature detectors. They could also be integrated into this larger perceptual scene within the current situational model, where we have multimodal representations. We've talked about, in recognition memory, we've talked about declarative and transient episodic memory as another launch memory system. We've talked about two different kinds of codelets, structure building codelets and attention codelets. We've talked about how structure building codelets could build representations, and attention codelets could advocate for particular representations. So in this next phase, I'm going to talk about the attention phase. And we're going to kick that off with a diagram starting with our attention codelets. So as I mentioned earlier, the attention codelets, they have some particular concern, whatever it might be. It could be a specific concern like, oh, I care about cars, or it could be something that's more general, that's the most activated structure. Attention codelets would bring some content and say, okay, these preconscious representations are what I care about. Coalitions could then be formed from that content, and they'll compete within a module called the global workspace, where the coalition with the highest total activation wins that competition and then gets broadcast out to all the different modules. This is the attention phase. Again, the actors in this are the attention codelets that advocate for particular content. Coalitions are formed from that content, and then some particular content within a coalition would then win the global broadcast and go to all these different modules. So next we're going to talk about procedural memory, and the first thing I'm going to do, because there's some terminology concerns here, procedural memory is not how to achieve a goal as we talk about it in LIDA. It has a different meaning. Bear with me, I'll try to make it very clear. But it's not like how to ride a bike. That's not what we mean by procedural memory. Procedural memory is long-term memory for how likely it is that an action will achieve a particular result when taken from the agent's current state, which we call the context. We take these different components and we combine it into a data structure that is called the scheme. And this terminology is inspired by Gary Drescher's schema mechanism, but schema was changed over to scheme because of trying to avoid some of these terminology conflicts. But let me try to illustrate this with an example, because I can see how this could be very confusing. So I'm an autonomous agent, and I pull up to the drive-thru at Taco Bell. And my desired result is that I want a 7-layer burrito. So I know from my past experiences with Taco Bell that if I order a 7-layer burrito, I've got about, let's say a 70% chance of actually getting a 7-layer burrito. The other 30% of the time, so let's say 20% of it, I might get something that's closer to a 5 or a 6-layer burrito. And then other times, I might get something like a chalupa or something else. You just don't know. Different results, same action, different result. Now, I might also realize that, well, sometimes I might order a cheesy bean and rice burrito, and sometimes I get the desired result of a 7-layer burrito. Not reliably, maybe just 10% of the time, but sometimes that same result happens from a different action. What these schemes do is it encodes the relationship of, if I'm at Taco Bell in the drive-thru, and I try to take these different actions of, I'm going to order a 7-layer burrito, or I'm going to order a cheesy bean and rice burrito, or I'm just going to drive off. What is the likelihood, which is quantified by this base level activation, of actually getting the result that I want of the 7-layer burrito? So the way this works in terms of, we've got the global broadcast that we've talked about, the conscious broadcast. So this conscious broadcast comes over to procedural memory. We have a set of schemes over there. Based upon the similarity between the conscious broadcast and the context of the schemes, and or the result of the schemes get activation. The ones that are over some threshold of activation become candidate behaviors, which are then sent over to the action selection module, which I'm talking about next. Okay, so action selection, the whole idea of action selection is you've got many different candidate behaviors. We've got to figure out how to find one behavior that can be executed later. So Again, this comes from procedural memory. The candidate behaviors come from procedural memory. We usually talk about Patty Maz's behavior net as a potential implementation of how we choose between different behaviors. I'm not going to go into the details of the behavior net, but imagine that this competition between these different candidate behaviors might include things like, first off, its relevance to its current situation, or it might include some things about the value, how much you want a particular thing, which we quantify with something called incentive salience that could have been brought in here. It could be even as complicated as looking at conflicts or any kind of consequences of these different actions. But at the end of it all, a single behavior is selected. And there's several different places this behavior goes to. First off, the sensory motor system, which is involved with the actual execution of the behavior. That's probably the first and foremost thing that is important about this. But in support of learning, there's a couple other things that happen with the behavior. It goes over to our attentional memory system, which is basically just the memory system around our attention codelets. And it spawns an expectation codelet. This is a special kind of attention codelet that's just looking for the desired result. It looks at the current situational model and says, did I get that 7-layer burrito? Did I get that 7-layer burrito? If it happens, then it says, ooh, we probably should bring this to consciousness. The other place is procedural memory, and I'll talk more about this later on, about how this is used, but the selective behavior does go back to procedural memory in support of learning.
I have a question.
Sure.
Some people might, in the old behaviorist day, call this discrimination learning, where you have a discriminatory cue, and if you perform an action, you get a result.
Okay.
And that is reinforcement, So what is additional here is some claim about consciousness, like when you, and maybe also making a selection of one action. Is that what may be over and above discrimination learning?
Well, so I guess we're going to get into more detail about this later on. We don't use the term discrimination learning, but there might be some similarities. So we talk about selectionist learning and instructionalist learning.
Mm-hmm.
Selectionist learning relates to changing what we usually call base level activations on structures, but it might relate to reliability or usefulness, utility, whatever you want to say about the structure. And then there's the instructionalist learning that's related to building new structures, learning new structures, like brand new concepts or brand new schemes that encode a new, context, action, results, observation from the environment. Within action selection itself, the learning, we haven't really fleshed out too much with action selection learning at this point. So in terms of action selection, I can't really say anything particular. But the structures themselves, the behaviors that are going to action selection, there's learning on those particular behaviors related to the